So the last video went through some background on light, but what we want to look at is how does that apply to chemistry, and more specifically right now to molecules that absorb light. So we're going to look at that light and how it is absorbed by molecules. So when we have a molecule, and it is just hanging out, doing its thing, nothing special or new has happened to it, it is in its lowest energy state, which is called the ground state. So it has the least amount of energy that it can have. That's its naturally occurring state. It's just hanging out, low energy, doing its thing in the ground state. Okay. When that molecule absorbs a photon, so we shine light at it, and that light, which is light is energy, right? We have the E equals h nu equation to look at the energy of a photon. So when a photon is absorbed by a molecule, it gains energy, and then that energy promotes the molecule to an excited state. It now has more energy than it did in its ground state because it gained energy. Okay, so that is absorption. So this picture here. The ground state is the bottom line right there. That's the ground state. So that's just showing that's the amount of energy that the molecule has in its ground state. And then that upwards arrow is showing when a photon is being absorbed. So the amount of energy increases, upward arrow, goes to a higher energy amount. And so each of the lines above are the excited states. They're amount of energy that are above the ground state. Okay, there are two arrows here, so we could absorb another photon and it would go up even further to have even more energy. Well, light, so if the molecule has this, it's in an excited state. It has more energy than it naturally normally does because it absorbed it. In order to get back down to the ground state, it has to emit that energy. It has to give away that energy. It has to release the energy so it can go back down to the amount of energy it had at the beginning. So absorption is when a molecule is gaining energy through photons. And emission is when the molecule is releasing energy, giving away energy, decreasing in energy to go back down to the ground state or to a lower state. So we see two arrows here that are pointing down. Okay. So it doesn't have to just go down to the ground state, but it can go down to a lower amount. So when that happens, it's releasing a photon. So the photons in absorption are going into the molecule, and in emission, the photons are leaving. So it's letting off light. We're going to get into that in a lot more detail in chapter 19. But for right now, knowing the terms absorption and emission are important. Knowing the terms ground state and excited state are important for us to start this conversation. So we're going to see these types of diagrams with these lines representing energy. You're going to see that on the energy, we don't typically, when we look at these diagrams, I don't put numbers to them, but they would each of these lines would represent a certain number of joules or kilojoules, which is typically joules when we're looking at this for a photon, joules that a molecule has. So this is just giving us a visual representation of light being absorbed to go from the ground state to the excited state, or light being emitted going from the excited state down to a lower energy level or to the ground state. So looking at the electromagnetic spectrum, which we saw in the last video, going from gamma rays down to radio waves, what we're looking at here is it kind of in a different perspective. When that light is being absorbed by the molecule, what happens to the molecule? It gets more energy, sure, but what does it do with that energy? Okay, so looking at this, we can see that microwaves, when a photon that is absorbed by a molecule, and that photon is somewhere in the microwave radiation, its wavelength and frequency are in the range of a microwave. What happens is that molecule gains that energy, and it uses that energy to increase its rotation. So spinning along the x-axis, the y-axis, the z-axis, or multiple of them. It spins, it rotates, okay? If the light that's being absorbed by the photon being absorbed by a molecule is in the infrared spectrum, we see vibrations. Okay, so we're going to look at those in more detail, but it's along the bonds. The bonds stretch and compress and expand, or they bend forwards or backwards. I'm making motions with my arms right now that you can't see, so it doesn't help. Well, maybe it can. No, I couldn't figure out how to get it to do it. I will figure it out in chapter 19 before we talk about these vibrations in more detail so you can see my wonderful hand gestures. But so vibrations are along along the bonds, either stretching, compressing, or bending. So that it takes more energy for a molecule to increase its vibrations than it does for rotations, because infrared light is higher energy than microwave light. And so microwave light is less energy, but it's enough to make it rotate. In the infrared spectrum, it makes it vibrate. What I need to add to that is it also has enough energy for it to rotate. So it would be vibrating and rotating at this point. As we move along, when we get to the visible and the ultraviolet spectrum, I guess I should change my color again. So visible and ultraviolet. So the light that we can see and light that we cannot see but is in the ultraviolet range, we see electronic excitation. So that's what this is saying. So what that is, back in Gen Chem 1, you wrote electron configurations, 1s2, 2s2, 2p6, 3s2 kinds of things. Well, we looked at in Gen Chem 1 some excited electron configurations where they wouldn't follow the pattern. An electron has moved to somewhere that it's not following the pattern. So 2s2 or 1s2, 2s2, 2p3, 3s1. Well, looking at that, whoa, buddy, we have to fill up, according to this, we have to fill up the previous electron configuration, the orbital first, before that electron can move. Well, this is an excited electron configuration, and this is for an atom, not for a molecule. Okay, so I'm kind of simplifying things a little bit. These electron configurations, the way they're written here, are for atoms, not for molecules. But the fact that this should be 1s2, 2s2, 2p4, that would be the ground state electron configuration. The excited state electron configuration is an electron has been promoted to a higher orbital, to a higher energy level. That's electronic excitation. Electronic means electrons. The electron has been excited to a higher orbital, to a higher energy level. These images, the pictures that we see here, are the molecular orbitals, the orbitals of the molecule instead of an atom, and we're going to look at that in chapter 19. But the ultraviolet and visible light is enough to actually promote an electron to a higher energy state, which is enough to it changes its shape. Remember the linear, trigonal planar, tetrahedral, trigonal bipyramidal? Promoting an electron is enough to give it a different electron domain, which changes its shape. So this is significant. We would be able to recognize that this has happened. So in the visible, if you shine ultraviolet or visible light at photons at a molecule, we would see an electron move up to a higher energy level. But that is even more energy than infrared and microwave. So we would also see it increase in its vibration energy and its rotation energy. So what's happening is as we go this direction, we're just adding on top of them. So if something has enough energy to increase its vibrations, it also increases its rotations. Something has enough energy to do an electronic transition, it is also increasing the vibrational and the rotational energy. So looking at the next level of energy, X-rays, what we see are actually bonds being broken and electrons being removed, so making it an ion. So we're basically destroying the molecule at this point. So that's why X-rays are damaging to any living thing, because their energy is so great that we see it actually destroying molecules and ionizing them. And the issue with that is in a human body, if we ionize a molecule, we make it a free radical, which is very reactive, and it reacts with everything, and it's not a reaction that is natural to the human body. So that's when we see things like cancer, where we have very fast happening reactions that are not natural in the body that are causing bad things. So what I want from this image is I want you, and this is going to be something we're going to be looking at in the next couple of chapters, so that's why it's important for us to get it now. Knowing that microwaves have rotations. Infrared is where we see vibrations, but we also have rotations. Ultraviolet and visible is when we see electronic excitation, but we also have vibration and rotation. And X-rays, we see the bond breaking and ionization. We also could have the electronic excitation, vibrations, and rotations. It's just, so, it's just adding on to it. Gamma rays I don't have shown there. It's we're going to also have the bond breaking and ionization at that point. So be familiar with this, and we will continue to add on to it as we move forward. So looking at ultraviolet and visible, which is what we do in the lab most often, is shine visible light and ultraviolet light. You have labs this semester that go along with that. The iron lab, we're shining visible light at it. It was kind of an orangey red color. And then the ultraviolet was when we did or do caffeine, because that's a colorless sample, so we have to shine light at it, that is, in its range. So this is the quantitative way that we use light to relate to concentration using absorption spectrophotometry, which is chapter 19. So we're going to get in a lot more detail to that. But this is just the background of what the instrument looks like if we're going to quantitatively shine light at a sample and try to get information out of it. We have to have a light bulb. And then that light bulb typically, for the visible spectrum, is a white light bulb, meaning it lets off all wavelengths starting at 400, going 100, all the way up to 750. We have a monochromator, which all it does is it filters out the light except for the one wavelength we want. We have our sample right there, and that's when it absorbs the light. And then we have a detector that lets us know how much light was not absorbed, because we shine a crap ton of light at the sample. Some of it gets absorbed by the molecules, some of it passes right on through, and so we measure how much gets detected, and based on that, we're able to get a measurement. Okay, so B there is just the path length, that's the distance. P naught and P, that we see right here and right here, are the differences between the amount of light being shined at the sample and the amount of, that's the zero, the initial, the amount of light being shined at the sample, and then the P with no subscript is the amount of light left over that did not get absorbed. Okay, so based on that, the instrument makes a measurement. And one of the, I guess, units or the type of measurement it makes is transmittance, which is symbolized by a capital letter T. And it is just the ratio of the light left over divided by the light shined at the sample. So this is less than 1. It's a fraction. And the smaller number is going to be at the top. So you'd get a decimal out of this. We often see percent transmittance, which is just the same thing, but times it by 100 to make it a percent. So this is, a percentage value. So it's between 0 and 100, 100 being the maximum that it could be if no light is being absorbed by the sample. So this is still used as the most common unit in certain biology aspects, but in chemistry, we typically use absorbance instead of transmittance. Absorbance is related to transmittance, but what it's doing is it is actually going to be measuring, instead of so transmittance is looking at the fraction of light that does not get absorbed by the molecule. Absorbance is looking at how much light gets absorbed at the molecule, and it moves it over to a log scale. So absorbance, which is capital letter A, okay, it's defined as it's related to these fractional, the amount of light. So it's taking the log of the amount of light that we shine at the sample divided by the amount of light left over, which ends up being the negative log of T, because we inverse that, so that's where the negative comes from. And if we're looking at percent transmittance, this is the equation between absorbance and percent transmittance. So if you ever have to convert between absorbance and transmittance or absorbance and percent transmittance, these are the equations for us to do that. So absorbance is the measurement that we made using our instruments when we did this type of lab. Okay, so the absorbance of light is directly related to the concentration of the molecule that is the light is absorbing for. So this is the mathematical relationship called Beer's law. It's officially, it depends on the textbook, the Beer-Lambert law, but Lambert often gets ignored, and so it's Beer's law. So in this equation, capital A stands for absorbance. Okay, the lowercase letter b we actually saw earlier. That's the path length, so it's the distance, how wide the container is that the sample is in. So it's in things like centimeters. We're measuring the length of a container. C stands for concentration, and that can be in any unit: molarity, parts per million, parts per billion, grams per liter, grams per milliliter, milligrams per milliliter, whatever, a concentration unit. And then the little E looking guy, that little epsilon guy, is the molar absorptivity, or the extinction coefficient. What it is it's a constant that relates absorbance to concentration. So it's a value that makes this equation possible. Now that constant, that molar absorptivity or the extinction coefficient, you can call it either one, has to have units that allow this to cancel out. So absorbance is unitless. Okay, so absorbance is unitless. B is typically in centimeters, and C is in concentration. I'm going to go with molarity, but it will be whatever concentration unit. It doesn't have to be molarity. So that means the units for the molar absorptivity or the extinction coefficient need to cancel those out. So they're going to be inverse centimeters, because we have to multiply it by centimeters and they cancel. And then in this example, inverse molarity. What I have written here is the units are concentration inverse times centimeters inverse. Again, the concentration I used in this example was molarity, but it doesn't have to be molarity. So it's a constant. But about that, it's a constant for one molecule at a specific temperature using a specific instrument. So it's not much of a constant. It's a constant for you while you're doing your experiment, but it would be a different constant for your closest neighbor while they did their experiment. It would be a different constant if you did that experiment on a different day where the room is a slightly different temperature using a different instrument. So when we do experiments that require the use of Beer's law, it's always at least a two-part experiment where part one is make standards where we clearly know the path length, the B value. We clearly know the concentration, so that's why they're standards. We already know their concentration. And then we can very easily measure the absorbance, so that way you can calculate the molar absorptivity or the extinction coefficient constant, and then you take a solution where you do not know the concentration and test it. But job number one is always figure out the extinction coefficient value, because it's a constant, sure, but it's not a constant you can look up in textbooks. It's not a constant that you can just magically know. You have to determine it experimentally on the day at the temperature and using the instrument that you're going to do the rest of the experiment. Okay, so this is Beer's law. This is not an equation that I'm going to give you. I am going to assume that you know this equation, because it's going to be assumed at all higher level chemistry that you know this equation. But the values would have to be given to you, obviously, to do the calculation. So that would help you with that. So again, you would have seen this in Gen Chem 1, you would have seen this in Gen Chem 2, and then we have experiments that we use Beer's law with it. Now, I will tell you, and we'll reinforce this later, that the molar absorptivity or the extinction coefficient in the lab, we typically determine it graphically, where we put absorbance along the y-axis and concentration along the x-axis, where the slope is going to be equal to the extinction coefficient times the path length. Oops, come back. Like in the y equals mx plus b, y is a, x is c, b we're saying is 0, or we're ignoring it, m, which is the slope, corresponds to the extinction coefficient times the path length. Well, if you already know the path length, you can take the slope and put in the path length and solve for the extinction coefficient. So that's how we typically do this graphically, is we get a straight line from the slope. So we do multiple standards. So part A of the lab would be make a bunch of solutions, like 5 or 6 solutions where you know their concentration. Test them to get their absorbance, and then graph them to figure out the extinction coefficient. Once you know that, now you can test a solution where you do not know its concentration, because then C can be the unknown for this equation. So this is just showing an example of what a graph would look like. Absorbance along the y-axis, molarity or whatever concentration unit, does not have to be molarity, along the x-axis, and then we would use Excel to get us the equation of the line, where m would be the extinction coefficient times the path length. Now, I told you that it's either extinction coefficient or molar absorptivity. I typically use the term extinction coefficient because molar absorptivity kind of implies that the concentration is molarity, but it's not always. The other two graphs we see here are set up differently. If you look along the x-axis, it's different. It's wavelength, okay? So this is just showing that if we take a sample so each of these graphs, we see 3 lines on this thing, is just at a different concentration, is the differences between them. It's the same compound, same temperature, same instrument, but different concentration. So we can clearly see that the absorbance increases as the concentration increases, because the graph gets bigger along the y-axis. And what we can also see is that you need to pick a wavelength, because it absorbs at multiple wavelengths. So in order to do the experiment, we would choose one wavelength. And we're going to come back to that a little bit more, but that would be the lambda max, the wavelength. Remember, lambda stands for wavelength, where we get the best absorbance. So probably like either right here or right here, which would correspond to that wavelength or that wavelength. You would choose one, and then you would set the instrument to it. I would probably go with the first one. Yep, that's a super straight line. And then that would be the wavelength we would set our instrument to do our experiment, and we would leave it at that wavelength for the entire time. That wavelength is different for every chemical. Depends on its color or just its properties on how it absorbs. Okay. So let's do an example with doing Beer's law. So Beer's law calculation example. Again, it's not terribly difficult, but I just want to make sure we can handle it. That with Beer's law, this is our equation. So we need to read the question and pick out the values and what variable they go with, and then solve for whatever we're solving for. So it says to find the absorbance. So absorbance is what I don't know. Of a 0.001789 molarity. Well, hey, molarity is a concentration, so 0.001789 molarity. Remember, the concentration does not have to be molarity. It could be any value that's a concentration unit of some kind. Of a solution of a substance with a molar absorptivity. That's that constant, of 303 inverse molarity inverse centimeters in a cell with a 1.50 centimeter path length. So I don't know absorbance. The extinction coefficient or the molar absorptivity is 313 inverse molarity inverse centimeters. The path length is 1.50 centimeters. And the concentration is 0.001789 molarity. Before I grab my calculator, looking at the units, molarity and inverse molarity will cancel. Centimeters and inverse centimeters will cancel. So I will multiply these three numbers together. When I get my answer, I get 0.840. Absorbance is unitless. So that is my final answer. Because if you look, all the units canceled. Okay. So you would be expected to calculate using Beer's law. I could ask you to solve for any of the three variables. I would give you the values that you need, and you would math it. Okay, so Beer's law is glorious. The math is not terribly difficult, but let's talk about sometimes it doesn't work, and when does it not work? So one time it doesn't work is if the light is not monochromatic. What that means is you're not able to pick one wavelength and stick with the one wavelength. If whatever instrument you're using, the light source keeps changing what wavelength it is, it's not going to work. If your concentration is too high, or if you're so like too high where the instrument won't measure the absorbance is what happens. And usually that line is 0.01 molarity, but it changes depending on the extinction coefficient of the substance where that line is. It also doesn't work well if your reaction is at chemical equilibrium, especially if that chemical equilibrium is not product favored. And then if we have issues like the light, I mean, not only is the light not one wavelength, but if it's varying and it's like open to where the light bulb in the room is being impacted, like you can see that. So if we have stray light, it needs to be where the only light that the instrument is measuring is coming from inside the instrument. If there's a window open, that's bad. Also, it's a problem if the temperature is not constant, because remember that extinction coefficient, that molar absorptivity value, is temperature dependent. So if the temperature is changing while you do the experiment, that constant is changing while you're doing the experiment. But when we do our math, we just use one constant. So that's a problem. Okay. And so here's the lambda max. How do we figure out what wavelength to set the instrument to? Sometimes it's told to you, but we're becoming bigger kid chemists here. So it's going to be time when you have to figure that out on your own. So what you would want to do is you would measure a sample, like one solution, over a variety of wavelengths. Now these instruments, the instruments that are attached to computers already have programs that are set up for this. So they will give you this type of picture. And then you would be looking for the wavelength, like kind of at the top of the hill, like the highest absorbance. Now we got to be careful though, because we don't really want it to be too close to the limit of the instrument. So for example, the limit of this instrument is 200. So I wouldn't want it to be here, even though that's the top of the hill, because it's too close to like the end. So I'd be looking at this. I would probably go with right here. So it's the top of the hill. So like it gives us a good absorbance value, a big enough absorbance value to easily measure. and it has a very rapid drop off. Ideally on both sides would be good. So that way, if the instrument's off by a little bit, you know, it won't be off by a little bit, pretty much. So that would be what I would pick. We could kind of choose anything in here, but I would go with the top spot. So if I were to give you a graph like this and ask you what is the lambda max, what is the wavelength we should set our instrument at? You're looking for the top of the hill that's not too close to either sides. Okay, so this is just an example for potassium permanganate. This would look different for every compound. You run this with caffeine, and that's how the wavelength was determined for caffeine. So with a molecule, just as we're talking about it, the chromophore is the part of the molecule that absorbs light, and that'll be something that you look at a little bit in organic chemistry because it's usually a functional group. And so this is just giving you a table of, depending on what color we see with our eyeballs, which is the color observed, what color of light is absorbed, and what is the likely lambda max for it. So in the lab, we did kind of an orangey red solution, which means that the color of light that the sample is actually absorbing is the blue or blue-green color, because the color that is observed is the rest of the light that is not being absorbed. So what our eyeballs see is what colors of light the sample does not absorb. And then, you know, that's some estimated values for that. For us, it was 510 though, so it was off a little bit. It just gives you a range of, you know, where to start. So if you have a sample, you have no idea what its lambda max is, this kind of table helps you on what to tell the instrument to measure between. Okay, now this table only works for visible light. If we have a sample that absorbs ultraviolet light, our eyeballs do not see ultraviolet light. So we would kind of just have to measure the whole ultraviolet spectrum to see what would happen. Okay, that takes us to the end of chapter 18. Chapter 19 is a much larger chapter. Most of the stuff in there is completely new to us.